I've got all these friends that just together. This is miserable.
Okay, I think we should start. So good afternoon. So let's start the lecture. So this last lecture, we began to learn the first detail supervised learning algorithm, machine learning model, namely the decision tree, right? In the last lecture, we focused on introducing the definition of decision trees. What are decision trees? Anyone sure? Can anyone remember the definition of decision trees? Yeah. So decision trees are essentially kind of a hierarchical data structure to efficiently represent a large number of labeled training data, right? So the key idea behind decision tree is that we give up storing all the particular data instances. Instead, we try to partition the original data into multiple subsets. In each subset, all the instances are purely labeled. That means they have only one label, right? And then in that case, we do not need to store those data subsets anymore. We just need to store their label. And also we need to preserve how can we partition, how can we get this partition. So the ways to arrive at this partition is preserved as accumulations of feature testing, right? Which are represented in decision tree as some nodes and branches. Nodes correspond to features, and branches represent different types of feature testing. So this is a decision tree. And we also have learned the expressiveness of the decision tree hypothesis space, right? That means if I want to use decision tree as our function family to search over everything, how large is this family? So I have learned that decision tree hypothesis space is very large. It's very flexible. We give a simple example of Bloom function learning. Example, suppose our task is doing a binary classification, and all of our features are Bloom features or binary features. Then actually, our learning task is to identify a Bloom function of several Bloom variables. In this case, we have shown that decision tree actually can represent any Bloom function in a full Bloom function space, right? And also, I threw a question for you. That because in our previous lectures, the lecture before that lecture, we give an example that in this Bloom function learning case, if we use the full hypothesis space, that means your hypothesis space is too large, and it's very hard for you to identify just one Bloom function by using a limited number of training data. Then I want you to help me to address the question that is how decision tree learning algorithm can learn or can identify such kind of Bloom function, which are represented by decision tree using a relatively small number of training data. I hope after this lecture you can give me this answer. And then we talked about how to use decision tree to do prediction, right? How to do that.
Start at the root of the tree and follow that until you
Yeah, it's very simple, right? Start the root of tree and performing feature testing, and go to a branch where you pass that kind of feature testing, and you found a path. At the end of the path, you reach a leaf, right? And then report the label on the leaf as a prediction. It's very simple and very easy. So those are the content we mainly talk about in the last lecture. And at the end of the last lecture, we mentioned a little bit about the decision tree learning algorithm. Namely, how can we construct decision tree to represent a set of training data. So today, we're going to focus all the details, algorithmic details about this decision tree learning algorithm. And our learning algorithm is called Id3 algorithm, very classical but very old algorithm. It's based on greedy heuristics. Oops. Oh, I'm sorry. What's wrong with this? Okay. So also, I briefly introduced the history of the decision tree development. As we can see, the history of the development of decision tree is very long, right? And now, our learning to introduce the details of the Id3 algorithm, the decision tree construction algorithm, will based on this simple classification task. That is, how can I determine whether to play tennis outside according to today's weather condition? So to represent today's weather condition, we extracted 4 features: the outlook, the temperature, the humidity, and wind. And the outlook could be sun, overcast, and rain. That means we have 3 feature values for the outlook, right? And for temperature, we have 3 types of temperature: hot, mild, and cool. And for humidity, we have 3 levels of humidity: high, normal, and low. And finally, for wind, we have 2 types of wind: strong wind or weak wind. So given those 4 features, we want to predict a binary labels, right? Positive label means that I will decide to play tennis outside. Otherwise, the negative label means that I prefer to stay in home. And suppose we have collected 14, a number of training data sets which consists of 14 instances, and represent each day's weather conditions and also my decisions to play outside or stay in home. And for those data sets represent this table, right? And for brevity, we just use we capitalize the first letter to represent the feature name and feature values. For example, in the first row, the first instance, the feature value S in the column O represents the outlook feature value is sunny, right? And in the third instance, the feature value H in the T column represents the feature temperature is hot, right? Like eighth row, in the feature value H in the column H represents the humidity level is high. And finally, like 14th instance, the feature value S in the column W represents strong wind, right? So our objective is to construct a decision tree to represent this set of training data. And in addition, we further assume our data is processed in a batch fashion. That means in our construction algorithm, at any stage, we can access the full data set. This looks pretty natural, pretty intuitive, but I can tell you there are other types of data processing ways, like online processing. In online processing, that means you are not allowed to access the entire data set. At any time, you are only allowed to access only one data instance. Then in that case, if you still want to construct the decision tree, then the algorithm design will be totally different. Right now, let us just focus on the batch data processing case. And let me first show the learned decision tree here. So this is our decision tree constructed by the Id3 algorithm. So, generally speaking, the Id3 algorithm is essentially a recursive partitioning process. That means we start to partition the whole data set. And over each partition subdata set, we recursively partition those subdata set again and again until every data subset we have all have the same label. Then we stop the partitioning procedure. And then during this recursive partitioning process, this decision tree is constructed from top to bottom. So this is the general idea of the decision tree construction learning algorithm, Id3. So now let us look at the detailed algorithm steps. Let us make a function name, this algorithm or function name. So let us first look at the parameters or inputs of this algorithm. So we have 3 parameters. The first parameter is S. That is the current set of examples or instances. Right? Because we're going to do the recursive partitioning, right? So we must have the input being the current data set to be split up, right? And then second parameter is the label. Namely, the labels for each instance in set in S, right? And third parameter is the attribute set or feature set. We're gonna select one attribute from this attribute set to split our data. So this is 3 input parameters for our Id3 algorithm. So now let us look at the algorithmic steps. So because this algorithm is recursive, so when you design a recursive algorithm, what kind of problems do you think you need to first resolve?
Base case?
What?
You need to know your base case. You need to know when to stop.
Right. Yeah. Are you from CS department? Yeah. I think it's reasonable. Yeah. So recursive algorithm is doing what? It keeps calling itself and calling itself until the stopping criterion is met, right? If you do not specify the stopping conditions, then just keep it calling itself until your stack is overflowed. So when you design a recursive algorithm, the first thing you need to consider is the stopping condition, right? So what's the stopping condition for our decision tree construction algorithm?
When you find a pure class, the subset S is all the same class? Like
Yeah.
all the labels are the same.
Yeah, exactly.
Or if you've used up all your attributes and there's no clear distinction.
Yeah, very good. So let us first specify the stopping conditions. That is, if all examples have the same label, or as you just mentioned, the attributes set is empty, right? But this is kind of some corner case I didn't list it here, but it's very good. You mentioned that. I will supplement this condition in the slides. Okay, this is our condition. And then what should we do? We return a leaf node, right? Because the recursive partitioning procedure is the creation process for the decision tree, right? When we stop our partitioning, then we reach the leaf node of the decision tree. So what we should do is to create leaf node, right? And use the label of this set of examples shared as the leaf nodes label, right? And now what if all the examples have multiple labels? What should we do? We should consider how to split this data, right? Because this is now pure label. And correspondingly, we're creating new nodes and new branches in our decision tree, right? So for the tree construction, we first create root node for this subtree. So this should correspond to subtree. And then we should select an attribute that can split this data set, right? And maybe you will ask, what do you mean by select an attribute that can best split the current data set S? Let's just put aside these questions and focus on the entire algorithm steps, and then we'll return to address this attribute selection problem. So suppose now we have identified such an attribute which can best partition the data S. Then the next step, we use this attribute to do the partition, right? How should we do? We enumerate all possible values that this attribute can take. Then for each specific value, we create a new tree branch. This new tree branch corresponds to a feature testing that whether the attribute A equals to B, right? And then we'll collect the subset of data, right? We collect the subset of data where each instance has the attribute B being attribute A being of value B, right? So this is a data subset. So let us consider some corner case. What if SV is empty? What should we do?
We don't need to make a branch to it, so nothing.
This is one idea, one strategy. Any other idea?
Well, from last time, when we did leave something empty, that left us a hole in our predictions, so we probably shouldn't even allow that.
Yeah, it's closer. I prefer more to this answer. So consider a case that if SV is empty, then we do nothing. We do not create any branch. We do not. We do nothing. Then what kind of cases will we have? If you remember the example in the last lecture, we manually created a decision tree to represent a set of geometric objects, right? And in that case, for SV is empty, we did nothing for them. Then what's the consequence?
No prediction.
Yeah, there's no prediction for some specific test instance. If I have my memory is not wrong, I still remember that test instance is green triangle. And unfortunately, I cannot find a path from root to some leaf. Then our decision tree is kind of embarrassing, right? Because we cannot produce the predictions. So to avoid this such kind of case, for SV is empty, we still create a leaf node. And then what kind of label should we add? Because there is no data to support us, which can support us to make the prediction. And what should we do?
Maybe you can default to the label that's most common.
Yeah, that's pretty reasonable assumption and reasonable choice, right? So we use the most common label in the current data set S as our prediction, right? And in this way, we can generalize in the testing time, right? Even there are some test instances cannot be found in our training instance, we can still give a prediction. Right? So now, in most cases, SV is not empty. Then what should we do? We should consider to split, right? This is a recursive data splitting procedure. So how should we do the split? We call the algorithm again, right? This is a recursive algorithm. This is the definition of the recursion, right? It calls itself. And now let us look at the parameters, the input parameters for this recursive calling. So what's the input? What's the data set of data examples? So now we need to use SV instead of S, right? Because we're gonna split this data subset. And what attributes do we need to consider? What set of attributes do we need to consider?
Everything except the one we just split on.
Yeah, exactly right. What?
Because you just split on it, so you'll have an empty node if you do it again.
You just split on it, so the other branches will take care of all the other SV primes. You have one set of the SVs, and there's going to be other ones, but all of them should deal with the rest of the attributes.
Can I give us a more detailed answer?
If we don't remove it, the next time it will be the best one is the best attribute.
Why?
Because all the elements belong to positive points. A.
So actually, you can think of all the instances in SV. What's their attribute value A? Or what? How many distinct values of attribute A are in the instances in SV? Only one, right? You have only one. That's why. Why? Because SV is produced by splitting the original data S according to distinct values of attribute A, right? So each SV, in each SV, all the data instances have the same attribute value in A, right? Then how do you use this attribute to split again? You do not have distinct values. How do you split? Right? So it's not necessary to use A again, right? So just remove A from our attribute set, and we only need to consider the remaining attributes in the original attribute set to consider the next split, right? So this is the whole algorithm steps. It's very, very simple. At the beginning, we call this Id3 algorithm with the whole training data set and with the full attribute set, also with the full labels, right? And then when we do the splitting and we produce several data subsets and we recursively call our algorithm again to do the splitting over each data subset again, and do this again and again, and until we meet the stopping criteria, right? And during this procedure, we create the root nodes for the subtrees and branches along with each node. And finally, when we reach the stopping conditions, we return leaf nodes, right? And in this way, our tree is constructed from top to bottom, right? So it's very simple. And I think every of you should be able to implement a decision tree algorithm by following this piece of pseudocode, right? So the remaining things, the remaining unclear thing is that how can we select the appropriate attribute that best splits the data set S, right? So to answer this question, let us first think of a problem. This problem that I have mentioned in the last lecture. So given the same set of training data, obviously there could have many decision trees, and each decision tree can represent data well. So among all of those decision trees, which decision tree do you think is the best? Don't look at slides. Think by yourself.
Least leaf. The one that's least ambiguous, so you could split the tree so that it might be fuzzy as you get towards the leaf nodes if you split it in a weird way.
I'm not very clear.
A tree whose classification is most likely to terminate early.
With the shortest path.
So you have to look at you're expected to look at the least amount of attributes before you arrive at your decision.
Yeah, closer. So we should choose the smallest decision tree, like in terms of branches, in terms of depth. So why? Because this is consistent with this famous principle called Occam's razor principle. So basically, Occam's razor is kind of a philosophical principle that is widely used and widely accepted in developing scientific theories or hypotheses. So suppose to explain some phenomenon or observations, you have developed a bunch of theories or hypotheses, and each of them can well explain this phenomenon or observations. Then there's a question, how should we choose among those different hypotheses and theories, right? Occam's razor is kind of a principle and tell you that you should choose the simplest theory or simplest hypothesis, or the least complex hypothesis or least complex theory. And as we will learn in the subsequent lectures about the computational learning theory, we will see that how the outcomes result is reflected in our mathematical characterization of the generalization performance among different machine learning algorithms. And we will see the more complex your machine learning model or algorithm is, the bigger penalty will be added on your generalization bound. That means too complex models will hurt their generalization performance. So this can be theoretical proof. So to be consistent with Occam's razor's principle, our goal of decision tree construction should be make our trees as small as possible. But is there a way to directly help us to find out the globally minimum decision tree? Unfortunately, this is a computation in physics, because finding such kind of tree is going to be hard. You have to enumerate all possible feature testing orders, right? This the permutation, the number of permutations will grow tremendously along with the growth of your feature number, right? So it is unrealistic.
I have a question. So as small as possible, is the small means the height of the tree?
Height, wide,
Both.
both. Yeah.
I think it would just be the smallest number of nodes, right? Well, no, that's not.
Well, here I'm not able to give some like mathematical definition of the smallest trees, but just keep in mind this kind of small. And later, in our later lectures, we are talking about the generation bound of the different machine learning models. There is kind of a mathematical metric to characterize the complexity, or in other words, how small this tree is. It's called basic dimension. But right now, let's just keep in mind that our goal in decision tree learning is to make our decision trees as small as possible. Right? So now that to find out the globally minimum decision tree is infeasible, then what kind of strategies can we have? We can use greedy search, right? Because we can use greedy algorithm, although this kind of greedy algorithm cannot guarantee the global optimum, but at least it can help us to very efficiently, very fast to find out relatively simple tree or small tree, right? This is how our recursive algorithm Id3 does, right? So let us review the total recursive algorithmic steps, right? We do not do backtracking. We start to identify one feature to do the split. Then after the splitting, we fix this feature, right? That means we fix the node of the tree. And then for all the remaining splitting data subsets, we try to identify the appropriate features to do the further split. After they are identified, they are fixed. We are now going back and to try them again, and to try another type like the second best feature to split, and then we'll try to split the subsets again, and then do a comparison. Although doing so might help us to find even better or even smaller decision trees. By doing that, you have to enumerate all possible cases, all possible permutations, right? This is called backtracking. But using these greedy algorithm steps, we actually fix the level of decision trees each time, right? We do not do backtracking, so the computation efficiency is very high. Is very high, right? So now comes the question. So the main decision algorithm is to select how to select the next attribute to split up, right? We must select such kind of attribute so that we can stop the partitioning of the data earlier, so that we can get a tree that is not that deep, right? As possible as we can, right? So how can we select this kind of attribute? So to answer this question, let us first consider a simple choices over only two attributes. And suppose we have these two attributes A and B. Both attributes are binary. And here are the training data sets. So for the case that A being 0 and B being 0, we have 50 negative samples. And for A being 0 and B being 1, we have 50 negative samples. And for A being 1 and B being 0, and we have negative 0 samples. And finally, for both A and B being 1, we have 100 negative samples. Now, given this training data set, can we decide which feature should we choose to do the first split?
Perhaps attribute B. If you were to split on B being 1 or 0, then I don't know. Actually, I'm not certain anymore.
Okay. So we can check, right? We can try to use A to split first, and then use B to split first, and say what is our resulted decision tree, right? So let us first try to split with A. So when we split with A, so we have two data subsets, right? For the first data subset where the attribute is value is 1, then we got 100 examples, and each instance means 100 examples is labeled as 1. It's pure labels, right? And when its value is 0, the corresponding data subset consists of 100 negative examples, also pure labeled, right? So both data subsets are pure labeled by splitting with the attribute A. So if we further construct the decision tree, what should we do? We should stop, right? Because the two data sets are pure labeled. And now, what if we split with attribute B? For attribute B, when the B's value is 1, the corresponding data subset consists of 150 examples, right? And among those 150 examples, 50 are negative, and 100 are positive. So this data subset is not pure at all. It's largely mixed. Then to construct our decision tree, what should we do next? We have to further split, right? We have to further split over this data subset. Of course, for this data subset where B is 0, then we have 50 negative examples, quite pure, so we do not to expand here anymore. But what can we conclude by comparing the splitting orders with A or B? So what kind of attributes should we prefer to do split?
Split them the most. Want to split them purely faster?
Yes. The pure is better, right? The pure your splitted data subsets, then the more likely that you can reach the leaf nodes, meaning that you can arrive at some data partitions which are purely labeled, right? So this kind of good heuristics for our algorithm, right? We can select those attributes that are after splitting with this attribute, then the pureness of the splitted data subsets are highest than using any other attributes. Right? This is a good. This is actually our principle heuristic to find out the best attribute to split the original data. So now let us change the data set a little bit. So we add 3 negative examples for the third case where A is 1 and B is 0. Shown is here. Then which attribute should we choose? We can take a look, right? So let us split with A first. So when A equals to 1, this data subset consists of 100 positive examples and only 3 negative examples, right? And when A equals to 0, the data subset consists of 100 negative examples. So it's still quite pure. Now, although it's not purely labeled as one label, right? But it's still quite pure. But what are the data subsets obtained by using B to split? We got 2 data sets. The first data set is largely mixed, right? And the second data set, of course, it is pure label. So although it is a very simple case, we need to both split the 2 data subsets here, right? And so it looks like the result, the same tree, have similar structure. But what if we have multiple attributes, I mean more than 2 attributes here? Like we have C, D, E, F features. Then, in case that we want to choose, we want to decide to choose A or B to start, then which one do you prefer to use first?
Probably A.
Yeah, still A, right? Because A is pure, right? The resulted data set splitting with A is pure. So we expect that in the later splitting process, we can stop early, and we got a higher chance to reach the leaf nodes early, right? So now we are clear. Any question about this?
How can we measure the pureness of the split when we have A, B, C, D, E, F, and it's hard to just see how pure the split is?
Yeah, that's a very good question. That's the question I'm going to discuss a lot. Another question. So, is anyone skeptical about this kind of idea or strategy? Okay, everyone agrees that using pureness to as an indicator or as some heuristic to help us identify the most appropriate feature to do the data splitting is the right choice, is the wise choice, right? And now comes the question, as this gentleman mentioned, how can we quantify the pureness, right? Only can we quantify the pureness of those splitted data subsets. We can rank those attributes, and then we can select the top rank feature to do the split, right? So now comes the evaluation metric or heuristic is called information gain. So before we introduce information gain, let us review our strategy for decision tree construction again. So our goal is to have the resulted decision tree to be as small as possible. And the main decision for our greedy heuristic algorithm is to select the next best attribute to split the data, right? And we want our attributes to split the training instances to subsets that are relatively pure in one label, right? In this way, we expect we are closer to a leaf node, right? This is the essence of the essential assumptions of our greedy heuristic decision tree construction algorithm, right? Then to evaluate this pureness of data subsets, we introduce the information gain principle, which is originated with the development of Id3 algorithm proposed by Kuhn. So to introduce the information gain, let us first review the concept of entropy. This is a very basic concept in the information theory. Is there anyone who has never heard of the concept of entropy? Okay, looks everyone is familiar with this. I'm happy with this. So, but let's just briefly review the definition of entropy. So first, let us give the entropy or purity of a set of examples with respect to the binary labels. So the entropy is calculated as follows. Here, P positive meaning the probability of the positive labels, and P negative is the probability of P negative of the negative labels. So the entropy is calculated as minus P positive multiplied with logarithm of the P positive, and then subtracting P negative multiplied with logarithm of p negative. So here, p positive is calculated by the proportion of the positive samples, right? P negative is the proportion calculated by the proportion of negative samples. It's very simple. And actually, in general, entropy can be defined over a discrete probability distributions. Like in this discrete probability distributions, we have k possible labels. And suppose each label k has probability pk, then the definition of entropy is here. It's very simple. It's just a summation over all possible labels. And each summation term is the negative probability of that label multiplied with logarithm of that probability, right? And from this definition, we can find some interesting observations or conclusions. The first is that if all the examples belong to the same label, then what is the entropy? Yeah, it's zero. Then tell me why.
Log of 1 is.
We can calculate, right? Suppose it is a simple case where p positive is 1, p negative is 0. Then this term, logarithm of 1 is 0, right? So this term is 0. And this term looks a bit troubling. Where's the mark? So for p minus, log p minus, although p minus is 0, but logarithm of 0 is negative infinity, right? But we can consider this term as some limitation of the sequence. We can consider that the limit we consider a sequence of real numbers that over the p minus. When p minus is approaching to 0, what's the limit of this sequence?
0.
It is 0, right? You can check it easily with some like Robida principle or whatever. It's very easy to prove this limit is 0. And this case is easily extended for multiple labels. So if all examples belong to the same label, the entropy is 0. And if otherwise, the probabilities for probability masses for all the labels are the same. Like for two cases, for the binary cases, p positive, p negative is 0.5, then the entropy is 1, right? And for key labels, the entropy is what?
What was the question again?
If we have a uniform distribution, I mean each label, its probability mass are the same, then what's the entropy?
1 over that many labels. Just for obvious.
It's logarithm over k, right? K is the total number of labels, right? So you can simply calculate. So from the coding theory and information theory, entropy can be viewed as the number of bits required on average to encode distinct labels. For example, if the probability for this positive label is 0.5, then we must use at least one single bit to encode both positive and negative samples, or negative labels. And if, however, the probability for positive is boxed, say 0.8, then we could prove that we can use less than one bit on average to encode the two labels. To see this why you can check out any coding theory book or information theory book. And now let me show you a few examples of entropies by in different setting of the probabilities. So here I listed 3 cases. In the first case, the positive probability is much larger than the negative probability. And second case, both probabilities are the same, 0.5. And third case is that the first probability is bigger than second probability, but it's not that big. Right? So what can we say from the entropy? We can say when P positive equals to P negative, the entropy is the largest, right? And when P positive is far larger than P negative, the entropy is the smallest, right? And the third case is in between them, right? And actually, we can expand these observations to multiple labels, and we will see that when the labels have the uniform distribution, we obtain the highest entropy. And here are these three cases again. So in the first case, the probabilities for different labels vary, right? Are different, but not vary too much. And the second case, the probability for all the labels are exactly the same. And third case, the probability for one label largely dominates the probabilities of all the other labels. Then we can look at their difference in entropy. So we can see for the uniform distribution case, where all the probabilities are the same, we have the largest entropy, right? And then when the probability of one label dominates all the other labels, that means all the probabilities for all the other labels very small compared as this label with largest probability. Then the entropy is the smallest. So from the entropy values for different cases, we actually can get another explanation of entropy. So entropy is kind of an indicator of the uncertainty. The more uncertainty, the high entropy you get. For example, in this uniform distribution case, you have most uncertainty about the label, right? Because each label has, any label can appear. They have an equal chance, right? But for this case, although you're gonna make some mistake, small mistake, but you have a very big chance to get a correct guess, right? So you have little uncertainty about what label will appear. So for low entropy, it indicates little or no uncertainty.
So is this log base K?
Yeah, log base K. You mean log 2 or log?
Well, I mean, so if K equals 2, then it would be log base 2.
It depends. If you want to use entropy to represent like coding theory aspects, because we assume we use binary, right? So it's log 2. But if you're use it in any kind of general information theory or information characteristic, then you can use any logs, whatever, it doesn't matter. So the absolute value of the entropy is not important. What we care about is relative. What's the relative difference between the entropy? Okay, so now, from the definition of entropy, what can we say? We can naturally use entropy to represent the pureness of a set of data sets, right? So the pure the labels in your data set, the smaller the entropy it has, right? Because we have less uncertainty about the labels, right? So that's how the information gain is designed. It is based on entropy. So the information gain is defined as, is for an attribute A, is defined as the expected reduction in entropy caused by partitioning or splitting with this attribute. So specifically, to calculate the information gain of the attribute A with respect to some data set S, we first calculate the entropy for the entire data set S. And then we'll subtract the average entropy of all the split data sets using this attribute A. So this is the definition of information gain. And to calculate the average entropy, and here we consider the size of each data subset. Why should we consider the size of data subset? Because we cannot guarantee our data sets are equally large, right? Consider using the attribute A to do the split. For one value like V1, you got a data subset which consists of 1,000 instances. And using the value V2, unfortunately, you got a data subset which consists only 10 examples. Then which data subset's entropy is more important? Yeah, the large one, right? Because the large one affects the quality of your feature on splitting the data set, right? So to consider this factor, we need to weight the entropy of each data subset by their size, right? So entropy of partitioned data with the attribute A is calculated by weighting the entropy of each partition by its size relative to the original set. So is anyone still, are there any questions about definition of this information game?
Is it going to be always positive?
What?
The gain is going to be always positive?
Yes, it's always positive. That's a very good question. And I may ask you to answer this question in the homework. We need to prove that y is always positive. Oh, no less than 0. Positive or equal to 0. That's a very good question. Okay, so now that everyone is clear about how to calculate information gain, right? Okay, let us try to calculate information gain and help us to find out the right features to split our data set, then to construct the first level of our decision tree. So I have 4 features in total, right? Outlook, temperature, humidity, and wind. Then we need to calculate information gain for each of these features and choose the one with the highest information gain to do the data split, right? So to calculate the information gain, what's the first step? Record the definition of information gain. Yeah, we need to calculate the entropy of the entire data set first, right? Because every feature's information gain requires that value. So let us first calculate the entropy for the entire data set. So we need to count the positive the number of positive samples, number of negative samples, right? So in total we have let's calculate negative 1, 2, 3, 4, 5. So we have 5 negative samples out of the 14 instances in our trained data. So P negative is 5 over 14, and P positive is 9 over 14, right? Then we can calculate the entropy of whole data set, which is very simple. Minus 9 over 14 times multiplying with logarithm of 9 over 14. Then subtracting 5 over 14 multiplied with logarithm of 5 over 14. Then it is approximately 0.94, right? And then let us calculate the information gain for the first feature, outlook. So how many distinct values of outlook do we have in this data set? All 3, right? The summing, the overcast, and rating, right? So then how many data subsets will we obtain by using outlook to split data? 3, right? Then let us look at the first data set where the outlook is summing. Then we'll have 5 examples in total, right? 1, 2, 8, 9, and 11. And among those 5 examples, how many examples are positive? 2, right? The 11th instance and the 9th instance. Then the positive probability is 2 over 5, right? And then correspondingly, the negative probability is 3 over 5. Then we can calculate the entropy for this data subset, which will follow exactly the same formula we used before, right? So this is 0.971. Now let us look at the second data subset, obtained by splitting the data with the outlook. This is a data subset where the instances attribute outlook as the value overcast. Then how many examples do we have? 4, right? The third instance, the seventh instance, the 12th instance, and 13th instance. Right? Then how many positive examples do we have? All 4 are positive examples. We got a pure label data set. Bingo. And the number of negative examples, therefore 0. Then what's the entropy? 0, right? And then let us look at the third example, which is rain, which corresponds to outlook being raining. So we still got 5 examples. And we can easily calculate the entropy is 0.971, which is equal to the entropy of the first data set. And now we have calculated the entropies for the 3 data subsets. Then we can calculate the average entropy of the 3 data subsets, which are weighted by the sizes of all data subsets, right? So the size for the first data subset is 5. So the weight is 5 over 14, right? And then multiply the its corresponding entropy 0.971. And the second data subset size is 4, but entropy is 0. So just ignore it. And the third data subset contains 5 examples, so the weight is 5 over 14. Then multiply the entropy 0.971. So we got our expected entropy here. It is 0.694. And then finally we can calculate the information gain, which is the entropy of the entire data set subtracting the expected entropy, right? And this is this is the information gain for our feature outlook. And we can follow a similar procedure to calculate the information gain for the second feature, humidity. So let us look at how many distinct values do we have for the humidity feature in this data set. 2, right? But how many distinct values does humidity feature have? 3, right? If you still remember our original problem setting, we have 3 humidity feature values: high humidity level, normal humidity level, and low humidity level. But in our data set, we only have 2 distinct values appearing, right? So in data split procedure, we got 2 data subsets. So let us first look at the first data subset where the humidity is high. So how many examples do we have? 7, right? We can take a look. The first, second, third, fourth, and 8th, 12th, and 14th, right? And among those 7 examples, how many positive labels do we have? 3, right? The 12th, the 13th, and 3. 3, 4, 3, 4, and 12, right? And then the number of negative examples is 4. We can calculate the positive probability and negative probability, and then calculate the entropy, right? And then for the second data subset, where the humidity is normal, we can see that there is 6 positive examples and only 1 negative examples, and we can follow the same procedure to calculate the entropy. So we can compare the 2 data sets. Which data set is pure? The second one, right? Because second one, there are 6 positive examples, only leaving 1 negative examples. But in the first data subset, the number of positive and negative examples are roughly the same, right? The difference is only 1. Then we can see their difference in entropy levels. So which data set's entropy is smaller, right? So this is one concrete instance. We can see how entropy can indicate the pureness of the data set. And then we can calculate the expected entropy for these two data subsets. Because these two data subsets, their sizes are the same. Both have 7 examples, so their weights are the same, right? And then here's the expected entropy. And then we can calculate the information gain, which is calculated by subtracting the entire data's entropy by the expected entropy, which is 0.1515, right? Then what is the information gain for the remaining 2 features, temperature and wind? We can follow exactly the same way to calculate the information gain, right? And here I ignore the detailed calculation and just list the values of those information gain. So according to the information gain, which attribute should we choose? Outlook, right? Because outlook has the highest information gain. And now we finish the determination or creation of our first node in our decision tree and the first 3 branches, right? This is our first level of decision tree, right? The attribute we created correspond to outlook feature, and 3 branches represent sunny, overcast, and rain, right? And for each feature value, we've got a corresponding data subset. Then according to our decision tree construction algorithm, what's the next step?
Do the same thing for each leaf.
Yeah, do the same thing, do the same data splitting process over all the 3 data subsets, right?
So if they have same value of the information gain, how to split?
Yeah, that's a good question. You can choose which one you want to do that. Because if you use information gain to measure the pureness, then there's no difference, right? But as we'll discuss later, information gain is not the only way to describe or characterize the pureness. You can definitely invent other ways to measure the pureness of your split data sets. Okay. So our next step is to recursively call our Id3 algorithm to split further on the 3 data subsets, right? And this process repeats until all the examples share the same label. Then we reach the leaf node and report label. Then until at that time, we can finish the decision tree construction, right? So then let us look at the 3 data subsets. So first data subset we need to be aware of is the second one. So how pure is the second one?
Completely pure.
It's completely pure, right? There's no distinctive labels. Then what should we do?
Terminate the node.
Yeah. Yeah, we terminate. Yeah. We create the leaf node, right? And then we use the label of those data set as the label for the leaf. And then finish the creation of this branch. And now let us take a look at this data set where the outlook is sunny. Right? So here's the data set. So what attributes set do we consider to choose for the splitting?
Humidity.
Yeah, these 3, right? Temperature, humidity, and wind. And now you can see why we cannot use outlook to do splitting, right? All the instances in this data subset share the same outlook value. They are all they are the same. They are sunny, right? Then how can you split? If you really want to split, your split is the original data set. That does not make any sense, right? So then we can follow exactly the same process as we just saw to calculate the information gain for temperature, humidity, and wind. And here we just ignore the detailed calculation, at least the information gain for the 3 features. And it turns out that the information gain for humidity over this subdata set as sunny is higher than the other two. Then what should we do? We split this data subset further based on the humidity feature, right? Then what kind of data subsets can we get using humidity to split? How many data subsets do we have? Two, right? Because humidity has two distinct values in this data subset. So each data subset are pure labeled, right? That means we do not need to split the corresponding data subset anymore. And we just stop the splitting and create a leaf node and using the label as leaf label, right? So third question. So do we finish the construction of this branch of the decision tree?
It's done.
Right? I mean, for this subset, for this branch of tree.
Not quite, we still have low humidity.
Um,
We still have low humidity to do.
Yeah, exactly. Yeah, very good. That's why I asked you, I want to remind you how many distinct features does this humidity feature have. Although in our data set, it only has two feature values appearing in our data set. But actually, our feature value have three distinct values, right? So there are some empty data set, right? Correspond to the low humidity level feature, right? Then what should we do?
Default to the most common one.
Yes, we'll create a leaf node for this empty data set, right? And then we use the most common label in this data subset as the label for this leaf. So what's the most common label in this data subset? Negative, right? So our label is no, right? So just keep in mind these small details in your implementation. Otherwise, if your friends use your implementation of decision tree to do prediction, you might be embarrassed because of those, those cases. What if your algorithm cannot do prediction for some test instances? How do you explain to them?
Can we just like normal everyday life implementation say that when we are labeling high humidity by no and normal by yes, then it makes more sense to label low also yes, no? Because normal is between low and high, and it's yes, so low should be yes too.
So you mean you want to?
I mean, not looking at the number of nodes we have, but intuitively, if I'm going to play tennis on a normal day, I should go for tennis on a low humidity day.
That's not necessarily the case. I mean, if it's really dry out, maybe you don't want to be running around because it hurts your lungs.
So I guess your suggestion is to consider the binary branches for each possible feature value, right?
Yeah.
High value, whether it is high, yes or no, right? Or whether it is normal, yes or no. Or whether it's low, yes or no, right?
Yeah.
This is a very great. This is a great thinking. This is something I want to talk about after I introduce all the details of decision tree learning. This is actually another way to create decision tree for the specific types of features. That means if our feature has multiple discrete values, so it is not necessary to expand multiple trees. For example, if to keep concise, to keep the tree structure to be concise, we can enforce our tree to be binary tree. That means every node you can only have 2 branches. Then how should we create the tree? Right? This is a way. This is one solution. And what you just mentioned is one solution. Yeah. So now let's just focus on this simple case, and then we can take a look at the third data set where the outlook is rain, right? And we can still calculate the information gain for this data subset. And it turns out the feature which has the highest information gain is wind. And the wind has only 2 distinct values. Right? So we do not need to consider the empty data set problem. And again, those corresponding 2 data subsets splitted with wind are both pure label. So we create leaf node and return the nodes, return and return the labels of the data set as leaf stable. So now we have constructed the whole decision tree for our training data in a classification of playing tennis task. So from constructing this decision tree, we have learned all the details about Id3 algorithm, including the ways to calculate information gain, right? So throughout this example, I hope every one of you will be able to implement your own Id3 decision tree algorithm. That actually will be included in the second homework, which will be released very soon. Very probably it will be released after Wednesday's lecture. And finally, to summarize, let's review the decision trees, everything about decision tree. First, from the representation perspective, what are decision trees? Decision trees are essentially a hierarchical data structure that represent the data or compress the data, right? And then in our learning of decision trees, the Id3 algorithm uses a greedy construction procedure. There are three important steps in Id3 algorithm. The first step is the stopping condition, right? If all the instances in the current data sets have the same label, then we'll create a leaf node with that label and return, right? Otherwise, if the instances have multiple labels, then we'll find the best attribute, say according to information gain, then use that best attribute to split the data for different values of that attribute. Then what's the third step? Recursion, right? We recursively do our Id3 algorithm on each splitted data set. Yeah, that's all I want to talk about. That's the most important parts I want to talk about the decision trees and decision tree learning. And the remaining big things I want to discuss, maybe I don't have time to cover in this lecture, is some extension of decision trees, which will mainly include a few tips and tricks when you build your decision trees on various applications or scenarios. For example, I want to talk about, the first point I want to talk about the variance of decision trees. As I just mentioned, to evaluate the pureness of the splitted data sets, you are not necessary to only use information gain. You can use other principles. And we will mention one example. And second, how can we handle examples with missing feature values? We will construct decision tree. Right? And third thing I want to talk about for those non-Bloom features, as this gentleman just mentioned, if our features have multiple discrete values rather than two, is the example we have just shown the only way to make the branches? Are there any other ways to make the branches in our tree construction? Right? And the fourth point I want to talk about is the important concept called overfitting. And you should keep in mind this concept during the learning of the all kinds of machine learning model and algorithms. Actually, the application of machine learning is kind of fighting against overfitting. You cannot make your model too complex to fit data too well. I will explain why. Okay, I think the time is up, and we'll discuss the remaining content in the next.